on number system to 1.1 introduction. So first कहते हैं, in your earlier classes you have learnt about the number lines and how to represent various types of number systems, numbers on it. जैसे नंबर लाइन क्या है कि ज़ीरो है, इधर नेगेटिव नंबर्स हैं, इधर पॉजिटिव नंबर्स हैं. सो ऑल दिस इज व्हाट टोटल, इसको क्या कहते हैं, नंबर लाइन कहते हैं. So just imagine you start from zero and go on walking along this number line in the positive direction. As far as your eyes can see, there are numbers and numbers. Now suppose you start walking along the number line and collecting some of the numbers. Get a bag ready to store them. You might begin with picking up only natural numbers like 1, 2, 3 and so on. You know that this list goes on forever. Why is this true? So now the bag contains infinitely many natural numbers. Recall that we denote this collection by the symbol n. Now turn and walk all the way back. Pick up 0 and put it into the bag. You now have the collection of whole numbers, which is denoted by the symbol W. Now stretching in front of you are many negative integers. Put all the negative integers into your bag. What is your new collection? Recall that it is the collection of all integers and is denoted by the symbol Z. Z comes from the German word zählen, which means to count. कहते are there some numbers still left on the line? Of course there are numbers like 1 by 2, 3 by 4 or even minus 2005 by 2006. If you put all such numbers also into the bag, it will now be the collection of rational numbers. The collection of rational numbers is denoted by Q. Rational number comes from the word ratio and Q comes from the word quotient. You may recall the definition of rational numbers. A number R is called a rational number if it can be written in the form of P upon Q. where P and Q are integers and Q Q is not equal to 0. Why do we insist that Q is not equal to 0? Notice that all the numbers now in the bag can be written in the form of P upon Q. P upon Q and Q are integers and Q is not equal to 0. For example, minus 25 can be written as minus 25 by 1. Here P is equal to minus 25 and Q is equal to 1. Therefore, the rational numbers can also include the natural numbers, whole numbers and integers. You also know that the rational numbers do not have a unique representation in the form P upon Q, where P and Q are integers and Q is not equal to 0. For example, 1 by 2 is equal to 2 by 4 is equal to 10 by 20, that's equal to 25 by 50 is equal to 47 by 94 and so on. These are equivalent rational numbers or fractions. However, when we say that P upon Q is a rational number, or when we represent P upon Q on the number line, we assume that Q is not equal to 0 and that P and Q have no common factors other than 1, that is P and Q are co-prime. So on the number line, among the infinitely many fractions equivalent to 1 by 2, we choose 1 by 2 to represent all of them. Now let us solve some examples about the different types of numbers which you have studied in earlier classes. Example 1. So are the following statements ट्रू और फॉल्स कहते गिव रीजन फॉर योर आंसर्स. तो फर्स्ट कहते every whole number is a natural number. So every whole number is what? 0 1 2 to like infinity. So false because 0 is a whole number but not a natural number. Second कहते every integer is a rational number. And the third is every rational number is an integer. So कहते हैं every integer is a rational number. तो कहते हैं true because every integer m can be expressed in the form of m upon n and so on. It is a rational number. Third is every rational number is an integer. So false because 3 upon 5 is not an integer. So example second कहते हैं 5 find 5 rational numbers between 1 and 2. We can approach this problem in at least 2 ways. The solution first क्या कहते हैं recall that to find a rational number between r and s you can add r and s and divide the sum by 2, that is r plus s by 2 lies between r and s. So 3 by 2 is a number between 1 and 2. You can proceed in this manner to find four more rational numbers between 1 and 2. These four numbers are 5 by 4, 11 by 8, 13 by 8 and 7 by 4. Solution second कहते the other options is to find all the 5 rational numbers in one step. Since we want 5 numbers, we write 1 and 2 as rational numbers with denominator 5 plus 1. That is क्या कहते हैं 1 is equal to 6 plus 6 and 2 is equal to 12 by 6. Then you can check that 7 by 6, 8 by 6, 9 by 6, 10 by 6 and 11 by 6 are all the rational numbers between 1 and 2. So the 5 numbers are 7 by 6, 4 by 3, 3 by 2, 5 by 3 and 11 by 6. The remark notice that in example 2 you were asked to find 5 rational numbers between 1 and 2, but you must have realized that in fact there are infinitely many rational numbers between 1 and 2. In general, there are infinitely many rational numbers between any two given rational numbers. Then let us take a look at the number or line again. Have you picked up all the numbers? Not yet. The fact is that there are infinitely many more numbers left on the number line. There are gaps in between the places of numbers you picked up, and not just one or two but infinitely many. The amazing thing is that there are infinitely many numbers lying between any two of these gaps too. So we are left with the following questions. What are the numbers that are left on the number line called? How do we recognize them? That is, how do we distinguish them from the rationals? The question will be answered in the next section. So exercise 1.1. So first कहते is 0 a rational number? Can you write it in the form of p upon q, where p and q are integers and q is not equal to 0? तो कहते yes, 0 is a rational number. It can be written as 0 by 1, 0 by 2 etc. in the form of p upon q, where p and q are integers and q is not equal to 0. And second question, that is find 6 rational numbers between 3 and 4. So to find the 6 rational numbers between 3 and 4, denominator should be made 2 equal to 6 plus 1, that is 7. Therefore क्या कहते हैं 3 is equal to 3 into 7 by 7, that is equal to 21 by 7. 4 is equal to 4 into 7 by 7, that is equal to 28 by 7. Six rational numbers between 3 and 4 can be found by varying the numerator between 21 and 8, or the numbers are 20, 2 by 7, 23, 24, 25 by 7, 26 by 7, 27 by 7. So these are answers. Third question, third is find for 5 rational numbers between 3 by 4 and 4 by 5. So to find the 5 rational numbers between 3 by 5 and 5 by 5, we may add the given numbers and divide by 2 and repeat the process. That is 3 by 5 plus 4 by 5 divided by 2, that is equal to 7 by 5 into 2, that equals 7 by 10, that is x1. Now for 7 by 10 plus 4 by 5, that's equal to this 7 plus 8 by 10, that is 15 by 10. Next rational number is equal to 15 divided by 10 into 2 is equal to 15 by 20 is equal to 3 by 4 is equal to x2, and next is 3 by 4 plus 4 by 5 is equal to 15 plus 16 by 20, that equal to 31 by 20. Next rational number is equal to 31 by 20 into 2 is equal to 31 by 40 is equal to x3. And next is 31 by 40 plus 4 by 5 is equal to 31 plus 32 by 40 is equal to 63 by 40. Get the next rational number is equal to 60 by 40 into 2 is equal to 63 by 80 is equal to x4. Get the 63 by 80 plus 4 by 5 is equal to 63 plus 64 by 80, that's equal to 127 by 80. And next rational number is equal to 127 by 80 into 2, that is 127 by 160 is equal to x5. So we got over on the x1 is x2, x3, x4 and x5. So कहते many answers are possible, therefore there are of course infinitely many rational numbers between 3 by 5 and 4 by 5. Next कहते state whether the following statements are true or false, give reasons for your answers. तो पहला कहते every natural number is a whole number. सेकंड कहते हैं कि एवरी इंटीजर इज़ अ होल नंबर. एंड थर्ड कहते हैं एवरी रेशनल नंबर इज़ अ होल नंबर. सो फर्स्ट देखते हैं इट इज़ एवरी नेचुरल नंबर क्या है, एक होल नंबर है. सो ट्रू सिंस द कलेक्शन ऑफ होल नंबर्स कंटेन ऑल द नेचुरल नंबर एंड इन एडिशन जीरो. एंड सेकंड कहते हैं एवरी इंटीजर इज़ अ होल नंबर. सो फॉल्स नेगेटिव इंटीजर्स आर नॉट होल नंबर्स. नेक्स्ट एवरी रेशनल नंबर इज़ अ होल number. So false numbers such as the 2 by 3, 3 by 4, minus 3 by 5, etc. are rational numbers but not whole numbers. So next कहते हैं irrational numbers. तो कहते हैं we saw in the previous section that there may be numbers on the number line that are not rationals. In this section we are going to investigate these numbers. So far all the numbers you have come across are of the form p upon q, where p and q are integers and q is not equal to 0. So you may ask, are there numbers which are not of this form? There are indeed such numbers. There are indeed such numbers. So कहते in Pythagorean in Greece, followers of the famous mathematician and philosopher Pythagoras were the first to discover the number which were not rationals around 400 BC. These numbers are called irrational numbers. Irrationals because they cannot be written in the form of a ratio of integers. There are many myths surrounding the discovery of irrational numbers by the Pythagorean Hipparchus of Croton. In all the myths, Hipparchus has an unfortunate and either for discovering that under root 2 is irrational or for disclosing the secret about under root 2 to people outside the secret Pythagorean sect. Okay, let us formally define these numbers. So a number is S is called irrational if it cannot be written in the form of P upon Q, where P and Q are integers and Q is not equal to 0. You already know that there are infinitely many rationals. In turn out that there are infinitely many irrational numbers too. Some examples are under root 2, under root 3, under root 15, pi, 0.100, so on. Remarks recall that when we use the symbol under root, we assume that it is the positive square root of the number. So under root 4 is equal to 2, though both 2 and minus 2 are square roots of 4. Some of the irrational numbers listed above are familiar to you. For example, you have already come across many of the square roots listed above, and the number pi. The Pythagorean proved that under root 2 is irrational. Later in approximately 425 BC, Theodorus of Cyrene showed that under root 3, under root 5, under root 6, under root 7, under root 10, under root 11, under root 12, under root 13, under root 14, 15, and 17 are also irrational. Proofs of irrationality of under root 3, 2, under root 3, under root 5, etc. shall be discussed in 10th class. And as to pi, it was known to various cultures for thousands of years. It was proved to be irrational by the Lambert and Lagrange only in the later 70s. In the next section, we will be discuss why 0.10110111101110 and so on and pi are irrational. Let us return to the question raised at the end of the previous section. Remember the bag of rational numbers. If we now put all the irrational numbers into the bag, will there be any number left on the number line? The answer is no. It turns out that the collection of all rational numbers and irrational numbers together make up what we call the collection of real numbers, which is denoted by r. Therefore a real number is either rational or irrational. So we can see that every real number is represented by a unique point on the number line. Also every point on the number line represents a unique real number. That this is why we call the number line the real number line. In the 1870s, the two German mathematicians Cantor and Dedekind showed that the corresponding to every real number there is a point on the real line, and corresponding to every point on the number line there exists a unique real number. Let us see how we can locate some of the irrational numbers on the number line. Example 3, locate under root 2 on the number line. It is easy to see how the Greeks might have discovered under root. Consider a square OAB and C with each side 1 unit in length. Then you can see by the Pythagoras theorem that OB is equal to under root of 1 ka square plus 1 ka square, that under root 2. How do we represent under root 2 on the number line? This is easy. Transfer this on the number line, making sure that the vertex O coincides with 0. तो कहते पहले हमने ड्रॉ कर लेना, दैट इज ये बनाना है, फिर इंटू 2 जो लाइन है दैट इज We have just seen that OB is equal to under root 2 using a compass with center O and radius OB. Draw an arc intersecting the number line at the point P. Then P corresponds to under root 2 on the number line. Next locate under root 3 on the number line. Let us return to figure 1.7. कंस्ट्रक्ट बी डी हमने यहाँ पे क्या बनाया था, दैट इज अंडर रूट 2. कहते हैं कंस्ट्रक्ट बी डी ऑफ यूनिट लेंथ परपेंडिकुलर टू ओ बी के परपेंडिकुलर हम क्या बनाना, बी डी बनाना है. देन यूजिंग द पाइथागोरस थ्योरम, then using the Pythagoras theorem we see that OD is equal to under root of 2 का square plus 1 का square under root 3. Using a compass with center O and radius OD, draw an arc which intersects the number line at the point Q. Then Q correspond to under root 3. In the same way you can locate under root n for any positive integer n after n minus 1 has been located. Now next is exercise 1.2. State whether the following statements are true or false. Justify your answer. पहला कहते every irrational number is a real number. So every irrational number is a real number. So this is true. All irrational and rational numbers together make up the collection of real numbers are. Next every point on the number line is of the form under root m, where m is a natural number. False example, between under root 2 and under root 2 there are infinitely many numbers and these can not be represented in the form under root m, where m is a natural number. Next every real number is an irrational number. False, all the rational numbers are also real numbers. Next are the squares of roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. The square roots of a positive integers are not irrational. For example, under root of 4 square root 2, which is a rational number. Next show how under root 5 can be represented on the number line. To represent under root 5 on the number line, we take a length of 2 units from O and from 0 and on the number line in a positive direction and 1 unit perpendicular to it. The hypotenuse of the triangle thus formed is of length under root 5. Then with the help of a divider, of a length equal to the hypotenuse of under root 5 units can be cut on the number line, that is this. सबसे पहले हमने so to represent the under root 5 on the number line we take a length of 2 units from 0, मतलब कि हमने 2 units का length लिया and on the number line in a positive direction and 1 unit perpendicular to it. ठीक है, पहले हमने नंबर लाइन पे 2 यूनिट का 0 ये 2, फिर 1 यूनिट का ये किया 1 और फिर ये जो ड्रॉ किया दैट इज दिस. तो ये क्या होगा 2 का स्क्वायर प्लस 1 का स्क्वायर का अंडर रूट दैट इज अंडर रूट 5. तो इसको फिर हमने क्या कंपास से हम क्या करें ड्रॉ कर देंगे, दैट इज कम्स आउट टू बी दिस विच इज द अंडर रूट 5. So fourth classroom activity. Classroom activity constructing the square. So फायदे take a large sheet of paper and construct the square root spiral in the following fashion. Get start with with the point O and draw a line segment OP of unit length. Get draw a line segment P1 P2 perpendicular to OP1 of unit length. Get now draw a line segment P2 P3 perpendicular to OP, then draw a line segment P3 P4 perpendicular to OP3. Continuing in this manner, you can get the line segment Pn minus 1 Pn by drawing a line segment of unit perpendicular length perpendicular to OP. In this manner, you will have created the points P3 P2, that is P2 dash P3 dash and so on, so P2 P3 so on, and join them to create a beautiful spiral depicting under root 2, under root 3 and under root 4. Next कहते real numbers and their decimal expansions. कहते in this section we are going to study rational and irrational numbers from a different point of view. We will look at the decimal expansions of real numbers and see if we can use the expansions to distinguish between rationals and irrationals. We will also explain how to visualize the representation of real numbers on the number line using their decimal expansions. Since rationals are more familiar to us, let us start with them. Let us take three examples, that is 10 by 3, 7 by 8 and 1 by 7. So pay special attention to the remainders if see if you can find any pattern. Pay attention to the remainders and see you can find any pattern. So example 5, find the decimal expansions of 10 by 3, 7 by 8 and 1 by 7. So first जब हम इसको डिवाइड करेंगे that is comes out to be 10 से डिवाइड किया 9 आ गया, that is this 3.3.3 so on आई जा रहा है, that is this. एंड जब हमने क्या क्या डिवाइड किया, जब हमने 7 को डिवाइड किया 8 से तो दैट कम्स 0.875, एंड जब 1 by 7 को डिवाइड किया दैट्स इक्वल टू 0.142857 एंड सो ऑन आई जा रहा है. सो कितने रिमाइंडर्स 1 1 1 सो ऑन, divisor 3 and divisor 8 640 and this. So we what have you noticed? You should have noticed at least three things. First, the remainder either becomes 0 after a certain stage or starts repeating themselves. Second, the number of entries in the repeating string of the remainders is less than the divisor. In 10 by 3, one number repeats itself and the divisor is 3. In 1 by 7 there are 6 entries, 3 2 6 4 5 1 in the repeating string of remainders and 7 is the divisor. Third, if the remainder repeats, then we get a repeated block of digits in the quotient. For 10 by 3 repeats in the quotient, and for 1 by 7 we get the repeating blocks 4 1 4 2 8 5 7 in the quotient. Although we have noticed this pattern using only the examples above, it is true for all the rationals of the form P upon Q. On division of P by Q, two main things happens: either the remainder becomes 0 or never becomes 0, and we get a repeating string of remainders कहते हैं let us look at each case separately कहते हैं case first the remainder becomes 0 तो क्या कहते हैं जो रिमाइंडर है वो जीरो होता है तो कहते हैं इन दिस एग्जांपल of 7/8 we found that the remainder becomes 0 after some steps and the decimal expansion of 7/8 that is equal to 0.875. Other examples are 1/2 that is equal to 0.5 and 639/250 that is equal to 2.556. In all these cases the decimal expansions